While it's frequently the case that we are willing to assume that when we have multiple sources of data and we're trying to run a hypothesis test comparing those populations, that the populations themselves are independent, this is not always going to be the case. And when it's not the case, we should be really cautious about the type of non-independence that we have, because depending on the type of non-independence, it's going to change our hypothesis test in different ways. Now, perhaps the most common way that we're going to violate that independence assumption is if we have what are known as paired data. So paired data are going to arise anytime that we have two populations that are being collected from, but those populations are really directly tied together. So we might be thinking about, for instance, taking two different measurements on the same individual, or you might be thinking about taking two measurements from individuals within the same family, or these types of things where there's going to be a dependence because of this natural relationship in the real world, but it's this specific type of dependence where one observation from our first population is directly tied to one observation from our second population. So, on occasion, interest is in comparing two populations' means when those populations are not independent, and the type of non-independence is actually going to matter. So, how can we think about the non-independent populations? Well, suppose that we have x1 through xn being drawn from some population. It's going to have a mean of mu x and a variance of sigma x squared. And we take y1 through ym drawn from a population with mean mu y and variance sigma y squared. So we have our two populations. We're observing values x and y from the first and second populations, respectively. Now, if x and y happen to be independent, then as long as we have a large enough sample, or if we're willing to assume that the populations themselves are normally distributed, we're going to end up with an approximately normal sampling distribution for the difference between our sample means. So x bar minus y bar will be approximately normally distributed with a mean of mu x minus mu y and a variance of sigma x squared over n plus sigma y squared over m. Now, this result is not going to hold if x and y are not independent of one another. And the way that it doesn't hold is going to depend on exactly what type of independence we're thinking about here. There's not going to be sort of one single result that we're typically relying on. Instead, we're going to think about, well, what type of dependence is there in these data? The most common type to think about are paired data, and so when we are thinking about collecting paired data, we're thinking about data that are going to be paired together, sort of naturally occurring in the world. So they're said to be paired if, instead of collecting two separate samples, we observe, say, x1 and y1 up to xn and yn paired together. We're thinking about them as being observed in some sense on the same unit or at the same time, or tied together in a way that is natural based on the context. So, as some examples, in biology, a biologist might be interested in the growth rate of plants before and after the fertilizer is applied. Okay. In this context, we are going to have paired data. The first measurement is going to be the growth rate before fertilizer. The second is going to be the growth rate after the fertilizer. These measurements are paired because they're taken on the exact same plant. And it's important to recognize that they're paired because, for instance, some plants likely grow faster than others, regardless of whether they have fertilizer or not. And so there's going to be this different growth rates, and sometimes we're going to be expecting some of those individuals, regardless of their fertilizer status, to be larger or smaller, right? So we have this pairing going on here. If we think about an example from medicine, we might have that a dermatologist is testing two different creams for addressing lesions on the same individual. And so in this case, we're applying two different results or two different medications to one individual. Each individual is probably going to react differently to any medication we give, and so it's not going to be independent, right? But the data are going to be paired. We have the first cream, we have the second cream, but each of these creams is being observed on the same set of individuals. And so we take individual 1, their first and second measurement, and those are paired together. Individual 2, first and second measurement, and those are paired together. In a business case, we might think about individual customers' opinions on two different product offerings. So once again, we're thinking about taking a set of customers, right, and we're asking their opinion on product A, and we're asking their opinion on product B. These give us two different populations, right? The opinions of A and the opinions of B, right? As the set of data that we're interested in. But each of our observations is going to be paired from sample 1 to sample 2. There's this natural correspondence between them where each customer is being asked their opinion twice. In a psychology context, we might think about measuring depressive scores before and after therapy for individual patients, right? And so again, we have a before and after. The same individual is being measured before, and then they're being measured after. So those are going to be innately paired, where that pairing is occurring within the individual. With paired data, we're often going to be concerned with our mean difference, right? So we're thinking about the difference of x minus the difference of y, and we can refer to that as delta sometimes. Now, one really critical thing to note is that if we were to think about taking our paired differences directly, and so we define this sample of d1, d2, up to dn, and d1 is just going to be x1 minus y1, and d2 is going to be x2 minus y2, and dn is going to be xn minus yn, right? So we take each of our pairs and we take the difference within those pairs. Now notice that as soon as we've done this, we have this single sample right here of the d's. Okay? And so these individual differences are going to represent univariate data. They're one sample at this point. And so if you had just been given the differences d1, d2, up to dn, this becomes a one sample problem for hypothesis testing. So ultimately, what we're going to realize here is that with paired data, we can actually convert the problem directly into a one sample problem by first considering, well, what are the differences between our individual data points? We use that to form this set of DIs, or D1, D2, up to DN, and then we're dealing with a single sample of what we call the paired differences. Okay? So this single sample is going to be analyzed in order to make inferences regarding delta, regarding the differences in the population means. So how do we think about this? Well, we need to try to work out, well, what is the sampling distribution going to be? And ultimately, the paired differences, if we form them, then as long as n is going to be large enough, the sample mean, which we can refer to as d bar, is going to be approximately normal, and it's going to have a mean that we can refer to here as mu d, and it's going to have a variance that we can refer to as sigma d squared, right? So mu d and sigma d squared. Now mu d is just the difference in these population means here, right? And so we had referred to that as delta earlier on. That's going to be exactly what we're interested in making inferences about. The variance of d is going to be a little bit more involved in terms of the variances of x and y. So we have the variance of x plus the variance of y, but then we have subtracting off 2 times this term over here, which is the covariance between x and y. Now the covariance between x and y is going to give a measure of association between x and y. And so it's going to be a positive number if they are positively related to one another. It's going to be a negative number if they are negatively related to one another. And then we're still dividing by the total sample size here, which is n. Okay, so covariance is representing, or cov is representing the covariance between x and y. We'll sometimes denote this with sigma xy to indicate that this is the covariance between x and y. And again, it's going to give this measure of association between x and y. If they are positively associated, so if as x goes up, we expect y to go up as well, then we expect a positive covariance. If they're negatively related, so as x goes up, y goes down, then we would expect a negative covariance. And if there's no relationship, then we should expect a covariance of around 0. Now we can make a sample covariance, which is sort of the equivalent quantity except based on the actual observable data. So we'll call this SXY, and it's going to look a lot like our sample variance. So we take 1 divided by n minus 1, and then we're going to sum over all of our data points. But instead of just taking, say, x minus its mean and squaring it, we're going to take x minus its mean and multiply that by y minus its mean. And so it looks a lot like that sample variance formula, but here we're using both x and y. Right? So the sample covariance here is going to give us a sample measurement of the actual covariance between x and y. Now, if we happen to know this variance or all of the components of this variance, then we can use a z-based procedure because it's a normal distribution with a known variance. More commonly, we're not going to actually know the variance, and so instead what we're going to want to do is use a standardized t statistic, right? So we can take our t-score here, which is our sample mean, subtract off the true mean, divide that by the estimated standard error. So SD here is going to be the estimated version of this variance. And if the mean that we plug in here is correct, then this should follow a T(n-1) distribution according to, or an approximate T(n-1) distribution. Again, as long as that sample size is large enough or the population mean is actually normally distributed. Okay, so how can we go about using our paired data then? Well, in order to conduct inference using our paired data, we're going to require estimators for both μd and sigma d squared. Now, if all of the data are available, then what we can actually do is we can just find our paired differences explicitly and then think about taking the sample mean and the sample variance of these, right? So we take the single sample procedures and we apply them to d1, d2, up to dn. This is going to give d bar or sd squared using our standard sample mean or our sample variance formula, and then we can plug in to our results there. Now, if instead of dealing with the raw data itself, we have our summary information, so we have information about x and about y, then it's important to be able to go from the summary statistics of x and y to the summary statistics of d. So we can estimate μd using d bar, and it turns out that d bar is going to be exactly x bar minus y bar. And in order to estimate sigma d squared, we can use sd squared, and this can be written exactly as sx squared plus sy squared minus 2 times the sample covariance, so sxy. Okay, so in this case, we're going to be able to use the sample analogs in place of our population parameters. If we want to find a confidence interval, right, so a 100 times 1 minus alpha confidence interval, this is going to take on the standard form of our t-based confidence interval here. So we'll take our d bar plus or minus our critical values, that's coming from the Tn-1 distribution with the level of alpha over 2, and then we take SD divided by the square root of n. So that's our standard error estimate there. For hypothesis tests, if we want to test whether the difference in means is equal to delta naught versus the alternative that it's not, then we can take d bar minus that null value, divide that by the estimated standard error, and under the null hypothesis, that's going to follow a Tn-1 distribution. Now, the same procedures are going to apply for asymmetric confidence intervals, so one-sided or otherwise asymmetric confidence intervals, as well as for one-sided or one-tailed hypothesis tests, right? So we can use all of the same T procedures and confidence intervals as we'd be able to in any other context using for paired data. So take a look at an example here, right? So in this example, we have a biologist that's investigating the effect of a new fertilizer on a plant growth rate. They measure the daily growth rate in millimeters of 10 different plants before and after applying our fertilizer. And so what we have here, right, is we have each individual plant. So we have our plants labeled from 1 through 10 here. We have the growth rate before they receive the fertilizer, and we have the growth rate after they receive the fertilizer. Okay. And so these data are all going to be naturally paired because for each individual plant, we have these 2 different observations. Those observations are going to be connected to one another, but it's connected in this very specific kind of way. And what we want to do is we want to test whether the fertilizer is going to impact the daily growth rates of plants using this alpha equals 0.05 level of significance here. Okay, and so the thing is, in this case, because we actually have our observations here for all of our data, we can come in and we can actually just use sort of a differencing approach, right? So what we're going to be thinking about here, right, is if we wanted to add in sort of this difference column down here, okay, so sort of write that in here, okay, then we'd be thinking about taking, say, the growth rate after minus the growth rate before, or we can do it as growth rate before minus the growth rate after, right? We'll either way, it's going to work. We're just going to end up with sort of a flipped sign. And so we might do, for instance, a 3 minus 2 here to give us a 1. We might do a 4 minus a 5 here to give us a negative 1, right? We can do our 4.5 minus 2.5 to give us a 2, and so forth through all of this. Okay, and then what we can do is we can take these observations that we have here and we can use them to actually test the null hypothesis that's of interest to us, right? So under the null hypothesis, we are going to be saying, well, the difference in their means, so mu d, is going to be equal to 0 versus the alternative that it is not 0. Okay, and of course, we can think about this hypothesis here as actually saying, well, mu x is equal to mu y. Right, so that's sort of the setup that we're thinking about here, right? And so our process is going to be, on the whole, first to find our individual differences, okay? And then second, once we have those, we can calculate our d bar and our sample variance, okay? And then for the third piece, we're going to want to calculate out our test statistic. And in this case, we're going to be thinking about that as being d bar divided by SD over the square root of n, right? And this should follow a Tn-1 distribution if that null hypothesis is actually true, okay? And so that's the basic framework that we're going to be thinking about going through here. And so now we can actually try to work on the specifics here. Right, and so here we're going to be taking our differences, right? And the differences we're taking after minus before. And so we get our 3 minus 2 giving us the 1, the 4 minus 5 giving us the negative 1, 4.5 minus 2.5 giving us the 2, 3 minus 1.8 for the 1.2, and so forth, right? All the way through the observations that we have. And so now what we're really thinking about is we're thinking about these observations that we have here as being one single sample from a single population, and we're running a hypothesis test on the basis of that data. Okay, and so we can walk through and say, well, we need the sample mean, and so the sample mean, we're going to take each of those observations, we add them all up, and we divide by 10, and that's going to give us 0.051. Okay, and then we are going to do the same type of thing to calculate out our sample variance. So remember, our sample variance, 1 divided by n minus 1. Then we sum up over all of the data here. We take the individual observations, subtract off the mean, which we just found to be 0.51. We square that. And if we walk through, then this is going to give us a variance estimate of 1.152. Okay, and so we can use that as our sample variance estimate here. And so then we get our test statistic and the actual observed value to plug in, right? We take d bar, subtract off the value under the null hypothesis, which we had determined was going to be 0, divide that by the standard deviation over the square root of n, right? The standard deviation is going to be given by the square root of 1.15221, right? Because this is our variance over here. And so then when we plug everything in here, we find a test statistic value of 1.502, right? And so that's going to be our observed test statistic. And now we can try to turn to our p-value here. Okay, and so for the p-value, because this is a two-sided hypothesis test here, the p-value is going to be 2 times our f at that computed test statistic there, where f is going to be our CDF of the Tn-1 distribution. Because n is 10, in this case, that's going to be the T9 distribution. Okay, and so we take 2 times the negative version of that test statistic. If we actually want to calculate that, we can turn towards R to do this for us. PT is going to give us the CDF, right? And so we take 2 times PT, we plug in the value that we've calculated here, we denote that the degrees of freedom are 9, and that gives us a p-value of about 0.17, for instance. Okay. So now we want to actually draw our conclusion, and we can state that because the p-value, which we found to be 0.167, is greater than the level of significance, we fail to reject the null hypothesis. Thus, there's insufficient evidence in the sample to conclude that the fertilizer is actually impacting the growth rate. Okay. Take a look at a different example here. The psychologist who's studying the efficacy for using CBT to treat depression, so they're considering a sample of 20 patients who had a mean depressive score of 18 with a standard deviation of 5 prior to CBT, and a mean depressive score of 12 with a standard deviation of 4 after CBT. The covariance between the depressive scores before and after was 15. Okay, and so here, if we think about, well, what are we actually being told? We have, again, these 2 different measurements, and so we can say that, say, X here is going to be our scores before, Y is the scores after, okay? And then what we're told, well, X bar is going to be the mean score before, so that's 18, and we have a standard deviation here of 5, okay? Y bar is going to be 12, and we have our standard deviation here of 4. And further, we're told that the covariance is going to be 15. Okay. Ultimately, we want a 95% confidence interval, but what we still need here is going to be d bar plus or minus t n minus 1 alpha over 2 times by the standard deviation of our differences over the square root of n. Okay? In order for us to get alpha is always 1 minus the confidence level, right? And so we take 1 minus 0.95, and that gives us 0.05, right? So we get our alpha here. We know that n here is just our 10, so that's all right. To get x or d bar, we note that d bar is simply going to be x bar minus y bar, right? So we can plug in our actual means here. Okay, so that is sort of our 18 and our 12. And again, we can choose whether we want to have this be the before minus the after or the after minus the before. Both ways are going to work. You're just going to end up either with a negative or positive sign, depending on which way you choose. And so then the last thing that we're going to need is to get SD, and the note that we'll make is that SD squared is going to be Sx squared plus Sy squared minus 2 times their covariance here. Okay. And so then plugging into that, we are going to be able to determine, well, what is the variance? We take the square root of the variance to give us our standard deviation, and then plug into our formula as we go. Okay. So we can walk through all of these sort of in the complete steps here. All right, so we'll take x here to be after in the solution. So then we have n is 20, x bar is 12, Sx is 4, y bar is 18, Sy is 5, and the covariance between them is 15. So d bar, which is going to be the difference between x bar and y bar, is 12 minus 18, which gives us our negative 6 here. If you had switched which one was before and after, you would have gotten positive 6, and that will be totally fine. We're going to get our variance, our sample variance here is going to be the sample variance of x plus the sample variance of y minus 2 times their covariance. So 4 squared plus 5 squared minus 2 times 15. That gives us a sample variance of 11. We want alpha, which is 1 minus 0.95, to be 0.05. And so the critical value here is going to be our T19 critical value because we have our 20 patients with a alpha of 0.05. And so then 0.05 divided by 2 is 0.025. I think when I was writing this down earlier, I was saying that the sample size was 10. Of course, that was from our last example here. The sample size is actually 20, right? So this should all be fine, right? We get that negative 2.09. If you actually wanted to get this for yourself, you can turn towards R using the QT command. It's going to give us our critical values from the T distribution. We want a level of 0.025. We want 19 degrees of freedom, right? So QT is going to always give us that. That will give us out that negative 2.09. And so then our confidence interval, we simply plug in d bar plus or minus our critical value times by the standard error. Plug that in, we get negative 6 plus or minus 2.09. The square root of 11 is going to give us our standard deviation because the 11 is our variance over 20 for our sample size here. And walking through, this gives us negative 7.55 up to negative 4.45. So that's our 95% confidence interval for the effect of CBT on these depressive scores. Okay. So it's worth thinking about using paired data and when we should use it and what we might want to be careful about. And so the first thing to note is that we should only consider the use of paired data if the data is actually justifiably paired, right? And so just because the data are the same sample size does not necessarily mean that they're paired, right? Just because you want the data to be paired does not necessarily mean that they're paired, right? The pairing has to have occurred in the collection of the data. It has to sort of be this natural pairing that's going on. And if you assume that data are paired when they're not actually paired, you're going to get erroneous results, right? So we can't just assume they're paired because the sample sizes are equal. A paired test is typically going to result in lower p-values than a non-paired test if we run it on the same sample. Equivalently, we could say that their confidence intervals are going to be less wide, and as a result, that makes these sort of an anti-conservative test in some sense. Okay. The other thing to note is that there are other forms of dependence that we might actually have that occur inside of our data, and if those types of dependence are actually going to start occurring, we really need to be addressing them separately, right? So pairing is just this single type that's sort of easy for us to address, and it comes up often enough that it's worthwhile to think about how to address that in its own regard. But other forms of dependence might arise, and in those cases, we might have sort of more severe violations of our test assumptions. Okay. Ultimately, The trick for dealing with paired data is recognizing that if we just take our differences, the paired data become a single sample. And then we can use single sample inference to address any of the paired questions that we might have, which makes that a very effective way of dealing with our paired data. Okay. So if data are naturally paired, then statistical inference can proceed by considering the single sample problem that arises from the paired differences. So we collect our individual samples from X, we collect our individual samples from Y, those are paired together. So we simply take those differences, and then once we're dealing with the differences, we're dealing with one single sample of data, which allows us to use all of the one sample inference that we might have at our disposal in order to answer whatever questions we might want to answer about those two populations.